Watch how this unstructured chaos snaps into a rigid sequence. Raw memory operates much like that fluid until we impose strict mathematical boundaries. Linear data structures are systems of organized sequential memory. We bypass rudimentary metaphors here to look strictly at system architecture. Stacks and queues possess massive computational power precisely because of what they prohibit. By artificially limiting our access to specific memory indices, we completely eliminate the need to systematically scan or shift elements within an array. The mathematical reward for this strict restriction is locking core operation times at O1 efficiency. O1, or constant time, denotes an operation that takes the exact same amount of computing time, regardless of the dataset's overall size. Constraining access paths is the absolute prerequisite for guaranteeing instant execution at scale in complex system design. An unconstrained raw array is functionally identical to a stack or a queue until we apply these specific mathematical boundaries. We enforce these boundaries using state trackers. Trackers are simply pointers that dictate the active, accessible limits of the data block. The mechanical requirements differ slightly. Stacks require a single state tracker, while queues demand a dual tracker system. The math of the pointers dictates the physics of the data. Manipulating these indices transforms a basic array into a highly specialized algorithmic engine. We define a stack by its strict LIFO constraint. LIFO stands for last in, first out, meaning the most recently added element is the only one that can be removed. This animated diagram illustrates a standard C++ array stack. Notice the pointer labeled top, initialized at -1, representing an empty state. During a push operation, the top pointer increments to index 0, inserting data directly into that specific memory slot. During a pop operation, the data is retrieved, and the top pointer decrements back down. The old data remains in the physical slot, but is structurally invisible. The peek operation functions as a strict read command, checking the top index without altering the pointer. The architecture fails through overflow when the array is full and the top pointer reaches the maximum limit, preventing new data entry. The opposing failure state, underflow, triggers if a pop operation is attempted while the top pointer drops back to -1. A stack single pointer design perfectly resolves depth. It mathematically forces the most recently opened operation to be the absolute first one closed. This LIFO constraint directly drives the system call stack. The call stack is a background mechanism that tracks active subroutines in a program, forcing deeply nested functions to resolve from the inside out before returning to the main process. Compilers use this exact setup for parenthesis checking. Reading left to right, any opening brackets are unconditionally pushed onto the stack. Encountering a closing bracket immediately triggers a pop, mathematically verifying that all operational dependencies are correctly paired. Stacks provide the fundamental architecture of nested dependency, ensuring that highly complex operations always maintain perfect sequential integrity. The queue operates under a completely different constraint, FIFO. FIFO stands for first in, first out. This diagram shows a queue built from a horizontal 1D array. Because FIFO logic interacts with both ends, a single pointer fails. We initialize two state trackers, front and rear, both starting at -1. For the Enqueue logic, the rear pointer increments to accept incoming data, while the front pointer snaps to 0, locking on to the oldest element. During subsequent Enqueue operations, the rear pointer advances rightwards to accept new data, while the front remains anchored. The Dequeue logic ignores the rear entirely. To process and remove the oldest data, the system simply increments the front pointer forward by 1. This reveals a critical structural vulnerability. Dequeue operations leave functionally dead space behind the front pointer. Queue failure states calculate the limits between these two moving targets. Overflow happens when the rear hits the maximum index, and underflow triggers if the front pointer overtakes the rear. Queues enforce sequential fairness and process breadth, but they require managing a shifting operational window to maintain constant time complexity. We see this architecture deployed constantly in system-level CPU process scheduling. A CPU relies strictly on FIFO logic to prevent resource starvation, forcing the processor to handle computing tasks in the exact order they are received. However, due to that dead space, a standard array queue will eventually trigger an overflow error as the rear hits the limit, even if the front is empty. While basic queues guarantee sequential execution order, their standard array implementations mathematically waste memory over time, demanding a structural evolution. In system design, encountering a rigid structural limitation immediately forces an algorithmic evolution. This animated diagram shows the mathematical solution to dead space, the circular queue. The flat array bends into a closed ring. We achieve this using modulo arithmetic, wrapping numbers back to 0 at a limit, allowing the rear pointer to overwrite abandoned indices. Further evolution yields the Dequeue, or double-ended queue, a hybrid variation that permits O of 1 constant time insertion and deletion at both boundary points simultaneously. Advanced data structures are not distinct inventions. They are iterative mechanical upgrades engineered to solve the inefficiencies of rigid constraints. This exact evolutionary logic scales up to one of the most highly tested technical interview paradigms, monotonic structures. This vertical stack illustrates a monotonic stack. It enforces a strictly sorted numerical order inside standard LIFO mechanics. Here, the stack holds numbers in decreasing order. To insert a larger element, like 9, the system forcefully pops smaller elements until the decreasing order is restored. This specific structural discipline is the absolute only way to solve complex algorithms like the next greater element problem in linear time. Linear time, or O of n, means the operation scales directly in proportion to the number of input elements. This same monotonic logic applies to queues, frequently deployed to solve sliding window maximum problems by mathematically culling useless data on the fly. We began with a raw array, applied pointer-driven boundaries to create stacks and queues, and layered on logic constraints to build monotonic architectures. In advanced system design, true algorithmic power comes not from infinite flexibility, but from the strict mathematical enforcement of boundaries.